right? So Paul says, let's change the rules. Now, the only rule that's not going to change is our starting condition. In other words, we still start off with 0. Other than that, we are going to introduce two changes. Firstly, we're going to time the game. We choose a time, t, and we play the game in that time t, which means that if we were to do 6 tosses, first of all, each toss would be done in a time t/6, and the bet size now needs to change also. No longer plus minus 1, it's now going to be plus minus root t/6. Right? So there's 6 tosses in this game. So the bet size is either going to be plus root t/6 or minus root t/6. In other words, Ri now is equal to plus root t/6 if it's a head, and minus root t/6 if it's a tail. Happy with that? And let's see what happens to the quadratic variation. So here's the quadratic variation. There's Q. This is still equal to plus minus root t/6. And if we open this out, what happens? We square this, we multiply it by 6, and we still have a quadratic variation of, before it was I, now it's t. Right, so we've introduced time into our coin tossing experiment, or game. So 6 tosses isn't very good. So change the rules of the game, again, to speed up the game. So let's choose some arbitrary number n. So what we now do is we still play the game in time t, but each toss will be done in a time t/n. So play the game, n tosses, so therefore the bet size now is plus minus root t/n. So shall we write down, it says with an amount, so we need to say plus minus. Clearly you can see that as n becomes larger and larger, firstly, the time that we have for each toss will become smaller, and the bet size will also become smaller. Agreed? So let's have a look. Again, so now what we're now doing is we're doing n tosses, so we go from j equals 1 to n. This is the quadratic variation. This is plus minus root t/n. So when we square it, as we've done here, and we note that there are n tosses, can you see the quadratic variation is still t? So it doesn't matter how many tosses we do, the quadratic variation is t, which means the variance will also be t. So you can see that we get this quadratic variation and variance being independent of the number of tosses in the coin. So we could do this 6 trillion times, right, as an example, of n becoming very, very large. But the variation, quadratic variation here is still t. It's still finite. So now Paul says make n larger, so in other words n tends to infinity. And this speeds up the game, decreasing the time between tosses. So we can see that what Paul says about the order, he talks about, so first of all, the time for each game is t/n. So that means that that behaves like 1/n, which is what's being said over here. Decreasing like 1/n. And the other bit, which is the bet size, root t/n, this is behaving like the order of 1 over the square root of n, which is this. Right, so these last couple of lines, but the new scalings, and by scaling, what Paul means is the adjustment we've done to the bet size and the time in which we're doing it. And again, we're doing this because no other choice will work. You can sit there and try and come up with other choices of bet size and the time in which you play the game. Either you will have a game which blows up, or one that collapses to 0. This is the only one that will give us a finite value of t. So this has been fixed because we know that we need something which is finite. Just like last week, remember delta y squared over delta t. There were 3 scenarios, remember? And we found scenario 1, I think, collapsed to 0, scenario 2 blew up, and scenario 3 was just right. Because delta y squared over delta t, so the question that you were asking, i.e. the fact that they're both the same order. So one might be 0.004, the other one, so that's 4 times 10 to the minus 2, the other one might be 2 times 10 to the minus 2. So the 10 to the minus 2 bits cancel out, then you're left with 4 over 2, which is 2, which is the constant. So that's what we're really saying, that they're the same size. If one was 10 to the minus 3, the other one was 10 to the minus 4, then we'd have a problem, right? So it's the same here. Now, if we were to do this, and we speeded up the game, what we'd end up with is the following. So the blue lines are supposed to be a bit like the very first slide, where we had about 6 tosses, right? Then we move on to the red line as we increase n, and then as we let n tends to infinity, so the green colored plot is the limit as n tends to infinity. And let me just zoom in for a second. Can you zoom in? So how do, okay. So let's zoom into the green one. Can you see something interesting? At every single point, every single time here, you've got this point there, there, all of these different points as you zoom in. Okay, so just remember that you have this kind of behavior at each point, like a hat or a thing down there. Right, even though it's continuous, it's got all of these points there each time. So what we've done is we just zoomed in. So there's a reason why I zoomed in, and you'll see why in a moment. So as we go to the limit n tends to infinity, the resulting random walk stays finite. We're guaranteed that because of t. And it has an expectational conditional on a starting value of 0, which was very, very important, basic rule of our game. And it has an expectation conditional on a starting value of 0 of, so first of all, the expected value of st is 0. So if we quickly expand this out, so let's say this is equal to, how do I, let's go here, right. So this is equal to the limit, so the expected value of, so inside here, what we've got is the limit as n tends to infinity of this thing here. So Ri, I equals 1 to n. This is what we've got. Remember? We know what the bet size is. It's plus minus root t over n. Now, let's do a bit of calculation here. I can take the limit out of the expectation sign. Okay, so if we do that down here, is equal to limit as n tends to infinity, and then let's take this inside here. And what does that summation equal? Well, the expected value is 0. Right, that's 0, so it doesn't really matter how you take the limit. In case you're wondering, how come we're allowed to take the limit outside? If you did first year analysis, you would have done something called monotone convergence theorem. That's where this has come from. Just in case you're wondering if I've done any fiddling around. Okay, so are you all happy with the very first one? What about the second one? Should we do that one? The second one, so I'm going to do that over here. It's just a case of trying to squeeze it in. This is equal to the expected value of limit as n tends to infinity of the sum of r, right, ri squared, like that. I goes from 1 to n. Now, in case you're wondering how come I haven't put a squared around the whole summation? This is the reason why earlier on I looked at Paul's working, where I said that the cross-term products, when you take the expectation, is going to be 0 anyway because they're independent, the coin tosses. So all you're left with are the squareds. So that helps us here. We don't have to worry about it. So if I take the expectation all the way inside, just like we did before, so let's take the limit out. Now, let me try and squeeze it in here. So limit as n tends to infinity of the expected value. How far have we got yet? So sum of I is equal to 1 to n of the expected value of Ri squared. Now, any ideas what that's going to simplify down to? The expected value here.
T by n.
T by n. Yes, because it's a half times root t over n squared plus a half times minus root t over n squared. So we'll end up with 2 lots of that. So you get a full t over n, but you've got n lots of t over n, so this will equal t. Happy with that? I want to write it down. I can. Shall I do it over here? So this is equal to limit n tends to infinity of n lots of, so in here you've got half root t over n squared plus a half minus root t over n squared. Like that. And that becomes t over n, and then the n's cancel out and left with t. So the beauty of this is that this particular scaling, which means taking the bet size of root t over n, means that we can now let n tend to infinity in any way we like, because the value is t, it'll never change. It'll always be t. It doesn't matter how you take limits. Just like last week, delta y squared over delta t. Once you got that constant value, it was a case of, it doesn't really matter how n tends to infinity. So this has been fixed in a special way to allow these properties to come out, because no other choice is going to give us a random walk which works. And as n tends to infinity, this limiting behavior is precisely Brownian motion. Okay? So let's just have a quick look at what's on the next slide, and then we'll go from there. All right, here we go. So the limiting process for this random walk, as the time steps go to 0, time steps meaning that t over n is becoming so small that what you've now got, you've gone from a discrete experiment to something which is continuous. As n tends to infinity, t over n tends to 0. Agreed? It's called Brownian motion, and we will denote it as xt. Now, I tend to use w, so we can either use, Mehmet says, isn't kn just another n? Let's have a look. I think some of our friends are trying to catch me out here by trying to come up with scalings which may or may not work. But if we make the reward square root of t over k times n, that one Uchi doesn't actually stand up. K over n, you can't have two different things here. K and z, it doesn't blow up. Isn't k times n just another n? Yep, thank you, Mehmet. And Uchi, yeah, has agreed. So what Paul does throughout his book and also his slides is he uses xt for Brownian motion. So xt for Brownian motion. You will have a lot of textbooks that don't use xt, but they use x subscript t. Many people will actually say that that's proper rigorous notation for Brownian motion, because that's how you write down a stochastic process, right? So the thing now we can say is that a stochastic process is a family of random variables indexed with time. And that's the reason why, if you go according to the definition of a stochastic process, you have to write it down like that. So whether we do this or that, it really makes no difference. But x subscript t simply means x is a function of t. Okay. So it's a family of random variables, and that's exactly what Brownian motion is. Brownian motion is a family of random variables here indexed with t with those statistical properties, i.e. mean of 0, variance of time. The other way that you can write this down is WT, and that's because it's also called a Wiener process. So Brownian motion is the same thing as a Wiener process, because Brownian motion was based on experimental observations by Robert Brown. Some years later, Einstein used Brownian motion to study diffusions, just like we did last week. We looked at diffusion equations, didn't we? And then some years later, Wiener process did Norbert Wiener, MIT, did a couple of things. Firstly, he proved that Brownian motion actually exists, and secondly, he came up with some of the basic mathematical constructions and theory. And that's the reason why we can also call it a Wiener process. So Brownian motion or Wiener process, exactly the same thing. And that's the reason why we normally write it down as WT. Paul uses X, makes no difference, as long as you remain consistent. And talk about the properties of a Brownian motion. First of all, we want to say that x at time 0, which we can write down as x0, is 0. Now, you may find that in some books they'll say with probability 1. Or in other books, it may say almost surely. So what that's really saying is that it's going to be 0 unless something very, very unexpected happens. And given its probability theory, that's the reason why people tend to say almost surely. Now, if you have a look at finiteness, this is more a description of what we've seen so far. In terms of properties, there's essentially 3/4 properties. Paul is really emphasizing here the importance of the bet size, the root t over n. Anything else wouldn't have worked. So the next property is continuity, which we can write down as this. So t being mapped onto xt is continuous everywhere. But think back to when I zoomed in to that random walk, the green colored one. Why did I show you those points? It's because I showed you that at some places it looked like that, at other places it looked like that. Now we know that anything like that point there on the top and this point there, the derivative doesn't exist. Right? So Brownian motion is continuous everywhere, but it's differentiable nowhere. Because how would you actually define the gradient at that point? Right? Would it be this? Would it be that? Would it be that? The same here. What is it? Remember, think back to what the definition of a derivative is. If the limit as delta x tends to 0 of ... provided the limit exists and is unique. Right? There's nothing unique about anything here. This is continuous everywhere. You can work out the gradient everywhere except at those points, the one at the top and the one at the bottom. So we always said that it follows the Markov property. That's how we can write that down formally. And next Tuesday, we'll talk about martingales. Quadratic variation we've seen. The other important property is the fact that these are normally distributed, Brownian motion. So let's have a look at this and I'll go through this. It says here that over finite increments, that the change in a Brownian motion is normally distributed with a mean of 0 and a variance of ti minus 1. In other words, what this is saying is that Brownian motion, in other words this, x ti minus x ti minus 1 is normally distributed with a mean of 0 and a variance of whatever the time step is. Now you may be wondering, well, why have I put an absolute sign there? It's just the general convention, even though we know that ti here is larger than ti minus 1. So normally distributed, mean of 0 and a variance of whatever the time step is. This allows us to write down that dx, in other words, dx, which is an increment in a Brownian motion, is normally distributed with a mean of 0 and a variance of whatever the time step is, dt. So we're going to use that particular version here. That. Any ideas why it's normally distributed? Well, think of the coin toss. Remember, what distribution does a coin toss follow? It's Bernoulli, right? But if we have an infinite number of them, then the central limit theorem gives us something which is normally distributed. Okay, so I think are there any more properties? Having built up these, the idea, can I just write down one more thing? Let's consider, so these are, they also have, the other property is that the increments are independent. So Brownian motion has independent increments. So for example, if I've got the following, if I've got dw1 is w t, oh sorry, it should be x, shouldn't it? If I do write w, just let me know because I'm actually used to writing w. dx1 is dx t1 minus x t0. This is going to be independent of dx2, which is xt2 minus xt1, which is going to be independent of dx3 is equal to xt3 minus xt2. So this is sometimes bundled together with the very last property on the previous slide. So if I just quickly go here, this should normally say that these are normally, that the increments are normally distributed. So Brownian motion has normally distributed increments which are independent, which is what we're saying here. The other thing we can also write down is, suppose I've got Brownian motion at two different times. So let's suppose I've got this. I've got time t is greater than s. Then we can say that xt minus xs is normally distributed with a mean of 0 and a variance of that. And we can write down the corresponding probability density function for that, using what we did last week. So the PDF for this we can write down as 1 over root 2 pi t minus s, remember the standard deviation, e to the minus, and over here we can write down whatever this is. So let's suppose, let me call that x, let me call that increment x. So I can write this down as x squared over 2 t minus s. Does that look familiar to what we had last week? When we solved the Kolmogorov equation using similarity reduction. Doesn't that look familiar? Why? Because this is normally distributed. 1 over the square root of 2 pi times sigma, which is standard deviation. So if the variance is t minus s, the standard deviation is going to be root t minus s, and then you've got e to the minus a half x minus 0 squared, because the mean is 0, over sigma squared, which is t minus s, the variance. So this is the transition PDF for a Brownian motion. So we actually ended up studying Brownian motion last week without actually formally saying that we were talking about Brownian motion. Now, this is our basic building block in stochastic calculus. This is our random variable, time-dependent random variable, or stochastic process, or stochastic variable. So if you think about y being a function of x, this is now going to be, all our functions are going to be functions of this thing here, x. So the next question we're going to ask is, what happens to everyday calculus under this framework? Now, let's have a look. These properties were very, okay, right. So, very important notation. So, the other thing that we need to say also is the following, that x behaves like this. So there's a Wiener process or Brownian motion. It's normally distributed with a mean of 0 and a variance of t. So we've seen that. The other important thing for me to say is that we can write down xt as a normally distributed random variable, which is phi, times the square root of the time, which is this. So what this is saying is, it's not saying that that equals Brownian motion. You can't say that. But what you can say is that the distribution that xt follows is the same as if you have an n01 number, which is what phi is. So let me actually make that quite clear. So phi here is n01. So what we're saying here is that you take a phi and you scale it with a square root of the time step, which is t. That has the same distribution or statistical properties as a Brownian motion. So this is what Paul is saying here. Think of dx as being an increment in x, i.e. a normal random variable with a mean of 0 and a standard deviation of that. Because rather than x, we're interested in dx, because we're going to be looking at stochastic differential equations. When you look at when you look at differential equations, we're interested in small changes, aren't we? So what we're interested in here is dx as opposed to x. So dx then can be written down as, so dx we can say has the same distribution as this. In other words, n0 dt. So these are all different ways of saying exactly the same thing. We're talking about the behavior of a Brownian motion or an increment in a Brownian motion. And on Thursday, you're going to be bringing your laptops in. The first thing I'll show you after we've done all the maths is how to actually simulate this kind of behavior on an Excel spreadsheet. All we need to do is, we simply need to simulate this, which is easy to do, and then multiply it by the square root of the time step. So from now on, we're interested in dx, and we also think of dx as phi times the square root of whatever the time step is. So we don't really say multiplied by, we say scaled with. I know Paul would have used that word quite frequently as well. A scaling or scaled with. We don't say multiplied by, we say scaled with. So here's a couple of plots. The blue one is Brownian motion. And then just to show you what a function of a Brownian motion might look like, Paul then said, well, let's just look at the square of a Brownian motion. So the red realization here, or sample path, is x squared. So the blue line represents x, this is xt, whereas that is xt squared. But in each case, he's saying that Each one represents a function. So can you see in each case it starts off at 0. So we haven't really actually said anything about finance. We're still really talking about the underlying maths here. We're getting there.